All right, everyone, we'll get started. So welcome to the next portion of the symposium, which is highlighting the best graduate research from across campus. So we'll have 5 graduate students present their research, all sorts of different facets, as you'll see how diverse the research interests of all these students are. So the talks are all supposed to be 15 minutes, about 12 minutes for the talk itself, and 3 minutes for question and answers. To all the speakers, I'll sort of give you an indication when there's about 2 minutes left, so at the 10-minute mark, and then I'll stand up at about the 12-minute mark so that we can all sort of be on schedule. So with that, let me start off by introducing actually one of my own students, Matthew Bowen. He's in macromolecular science and engineering, and he's going to be our first presenter. So take it away, Matt.
Okay. Hello, everyone. As Anish mentioned, I'm one of his students, and I'm here to present our recent work on durable superhydrophobic coatings. So superhydrophobicity, or extreme water repellence, or extreme water repellence is a property exhibited by plants such as the lotus, most famously. As you can see, water droplets beat up completely on these leaves and roll right off. And this is due to a combination of their hydrophobic chemistry and surface micro and nanotexture, as shown in this SEM. So over the past 2 decades, numerous studies have aimed to synthesize superhydrophobic coatings, as they have a broad range of applications, including stain-resistant fabrics, such as the one shown there, reducing frictional drag against the side of ships and leading to significant fuel savings. They're also excellent at reducing corrosion and chemical attack. And if patterned, such surfaces can produce inexpensive open-channel microfluidic devices. But in all of these cases, the problem is that their lifetime is limited by their mechanical durability. So that's why we're focusing on this characteristic. Briefly, I'll define a couple terms. So a liquid placed on a solid surface exhibits a characteristic contact angle based on the balance of surface energy, as shown here. And for water, this contact angle ranges from 0 for a very hydrophilic surface all the way up to 120 degrees as the surface energy is decreased. Obviously, 120 degrees is much lower than contact angles exhibited by superhydrophobic surfaces. And the reason for this, as I mentioned, is surface texture. So for any hydrophobic material, there exists a critical roughness above which air pockets can be stably entrapped underneath a liquid. And this is known as the Cassie-Baxter state. This state exhibits the highest contact angles possible and also mobility of the droplets. So as seen in this video, the surface on the right is in the Cassie-Baxter state, but the surface on, the other one, surface on the left is in the Cassie-Baxter state, and the droplet rolls off. Whereas if the liquid can penetrate into the texture, the drop is strongly adhered, even though both surfaces exhibit high contact angles and resistance to wetting. And the easiest way to characterize droplet mobility is roll-off angle, so you just simply tilt the substrate and measure the angle at which the drop rolls off. And we'll be using this method throughout the work. So, as superhydrophobicity is dependent on surface microtexture, it's very vulnerable to mechanical abrasion, as I mentioned. So previous attempts have focused on making the surfaces out of inherently durable materials, but these tend to be relatively hydrophilic and require hydrophobic surface treatments. And even if you use extremely durable materials, since the surface features are so small, they can still be sheared off under abrasion, revealing hydrophilic defects. So we use an approach in which we produce an inherently hydrophobic porous matrix, since even if the material is less inherently durable, the superhydrophobicity will be better retained if the bulk is hydrophobic. And we use spray deposition to produce these coatings because it's inexpensive and scalable. And the components we use are a hydrophobic polymer together with a low surface energy molecule, which is partially miscible with it. We theorized that this partial miscibility would produce a partially coalesced superhydrophobic texture, which is also inherently durable. Since we're studying miscibility, we needed a way to quantify this and to do this, we'll use Hansen solubility parameters, which essentially decompose the intermolecular bonding energy of any chemical species into its dispersion, polar, and hydrogen bonding components. And then for each of our coating components, we can identify its good solvents, which have known Hansen solubility parameters, and define a sphere in a space defined by these parameters that contains all of those solvents. And then for two components, we can define their miscibility by simply looking at the overlap of the two spheres. So basically, the number of common good solvents they have. And then for that, we define a simple geometric parameter which characterizes the overlap of the two Hansen spheres. So a completely immiscible pair will have no overlap between the two spheres and an S star parameter greater than 1. If the two components are completely miscible, S star is less than 0, and their spheres completely overlap. And in the intermediate regime, they're partially miscible. And again, this is the regime we predict will produce durable superhydrophobicity. So then we spray coated over 50 combinations with various S star parameters. This is an example of one of them on the right here. And we subjected all of these coatings to rotary chamber abrasion, which is an extremely harsh testing method used in industry to test organic coatings. And all of the commercial coatings that we tested lasted less than 100 cycles. So this is a particularly harsh test for superhydrophobic surfaces. As we expected, all of our coatings fell into one of those three categories. So either they were too miscible and formed coatings which were too smooth to be superhydrophobic initially, or they were too immiscible with high S star values, and they formed superhydrophobic surfaces which were loose particles on the surface, which could be easily wiped away. But surfaces with intermediate S star values, which were partially miscible, formed partially coalesced spray texture, as shown in this SEM, which could withstand at least 100 cycles of chamber abrasion. And all of the surfaces that we found to exhibit this property were between these ranges of S star. So looking at the abrasion in a bit more detail, so these are 3 commercial superhydrophobic spray coatings we tested from 0 to 100 cycles, and this is the roll-off angle on the y-axis. As you can see, they all catastrophically fail within 100 cycles. The immiscible superhydrophobic surfaces do a little bit better, but still wet after 100 cycles. But as seen here, one of the partially miscible superhydrophobic surfaces withstand this abrasion. And we can take a number of them and abrade them for significantly longer, so they all last well above 500 abrasion cycles. And again, they're all within this partially miscible regime and significantly exceed the performance of commercial superhydrophobic spray coatings. The other interesting property of these surfaces is that they can actually recover from damage. So we took one of these spray-coated surfaces, compressed it in a hydraulic press, so that it was completely smooth and not superhydrophobic. Then this is a video taken in environmental SEM as the coating is being heated at 100 Celsius. As you can actually see the superhydrophobic spray-coated texture actually recover. And this effect was also observed on extensively abraded samples. So if you take one of these surfaces, abrade it to 1,000 cycles, the roll-off angle is about 20 degrees, but then heating it briefly recovers the roughness and also drastically reduces the roll-off angle. The other effect we observed is that the surfaces could recover chemical damage. So oxygen plasma destroys surface chemistry, but not surface texture. But heating the coating again can allow free hydrophobic filler molecules in the bulk of the matrix to diffuse to the top surface. So the surface is initially superhydrophilic after oxygen plasma, but heating it restores superhydrophobicity. And this can be done repeatedly. So this is 10 cycles of oxygen plasma and then subsequent heating. Okay, so the combination of these two healing effects allows us to abrade the sample even more. So up to 5,000 abrasion cycles is shown here. And with periodic heating every 500 cycles. So this point highlighted here is one of the most durable coating that we found, even after 90% of the coating thickness is removed. As you can see in this high-speed video, a droplet impacting at high velocity can still rebound completely without wetting the surface. We also subjected this most durable coating to a number of other damaging exposures. One in particular is sandpaper abrasion, which is one of the most commonly used. One of the most commonly used testing methods in the literature because it's easy to perform manually, but we automated it and ran this process for over 1 kilometer of total length. We also exposed the coating to flame. As you can see, the coating was still superhydrophobic afterwards. And we also scratched it with a razor blade, which doesn't have significant effect. And various other tests, including rinsing with fluorinated solvents, acids, bases, very high temperatures, corrosion testing, and ultraviolet light. And in all of these cases, the coating either resists damage entirely or could be recovered after heating. So, to conclude, we found a way to systematically identify spray-coated durable superhydrophobic surfaces by identifying partially miscible hydrophobic components. And this is generalizable to multiple types of hydrophobic chemistry. So we found non-fluorinated and fluorinated blends which exhibited this property. The most durable coatings significantly exceeded the performance of a number of commercial superhydrophobic spray coatings. And any damage to the most durable coatings could actually be recovered by heating them. So with that, I'd like to acknowledge my coworkers and our various funding sources and the shared facilities that enabled this work.
All right, our next talk is going to be on the fundamentals and applications of organic, inorganic, hybrid semiconductors.
Thank you very much for the invitation to present here at the department's bicentennial symposium. I'm here from the Optoelectronic Components and Materials group to present our efforts to understand and apply hybrid semiconductors in optoelectronic devices. So the importance of dissimilar semiconductors integrated into the same optoelectronic device is underscored by their use in advancement of performance of optoelectronic devices. So just looking at the past half century, use of heterojunctions, which is where the dissimilar semiconductors meet, has led to a continuous reduction in the solid state lasing threshold up from 10 to the 5 kiloamps per centimeter squares to 50 amps per centimeter squared. There is the two-dimensional electron gas structures, which are used in our high electron mobility transistors, which do RF communications in our cell phones. And there is the in-gas detector, which is the backbone of a lot of the fiber optic communication that powers our information transmission infrastructure. So recently, in last 10 or 20 years, there's been an expansion of materials that we considered semiconductor materials. And organic, inorganic, hybrid semiconductors have become important in their in advancing applications of these materials. So to give you 3 examples, there is the Gratzel cell, the Dyson-sized solar cell, where the dye absorbs photons, and then you use the titanium dioxide to dissociate the photon into charge carriers. So you get a solar cell. In organic photovoltaics and organic LEDs, which are starting to get integrated in all our display technology, the metal oxide organic heterojunction is used to connect tandem PVs and tandem LEDs. Recently, the high-efficiency perovskite solar cells have been reported, and organic materials are used for charge transport there. And further, there has been some preliminary work on surface passivation of 3,5 Schottky diodes and nonlinear optical phenomena observed in hybrid semiconductor systems. So my goal in this work is to understand excited state phenomenon in organic and inorganic hybrid semiconductors and to apply them to advance optoelectronic devices. So if we look at the properties of organic and inorganic semiconductors, they originate fundamentally from the bonding characteristics that hold them together. So inorganics are generally covalently bonded, so covalently or ionically bonded, so that's a chemical bond. Organics, on the other hand, are formed into these carbon molecules that are held together by van der Waals bonding, which is a dipole-dipole mediated interaction. As a result, you can think of the organic as this basically like a quantum dot. So it has very high absorption, but the charges have to get from one molecule to the other. So there's low charge transport, charge mobility, because they have to hop. In the inorganics, you have band transport. The charges are able to zip right through the crystal. Of particular interest in this work is the excitonic properties. So organics have a tightly bound exciton, which is small radius, while inorganics have large radius exciton, which is loosely bound. So with that, let's consider organic and inorganic heterojunction and apply it to a solar cell application. So here I have an inorganic, and I have put an organic right next to it. And this is a band diagram, so we're looking at the energy as a function of position in the device. So in this device, if I want to operate it as a solar cell, I inject a little charge, a little photon in, and what the photon is going to do is excite exciton in the organic. So you have an exciton is a tightly bound electron hole pair, so it's stuck together, and it's sitting in the organic. And in the inorganic, as soon as I excite it, it results in free carriers because the exciton is loosely bound. So now you have this exciton which is going to diffuse around, and once it reaches the interface, the electron from the exciton is going to transfer over, and the hole is going to remain in the organic because of the energetic difference here. And we're going to form this slightly loosely bound hybrid charge transfer exciton, which is what I'm going to term it from now on. So the HCTE is the loosely bound state which mediates the dissociation. And if I inject charges from the cathode and the anode, that's also the recombination site, which happens through this HCT state. So on the right here, I've summarized the state diagram, and we find that the HCT is the central quasi-particle that's governing exciton and hole recombination in this organic and organic heterojunction. So just to help you visualize this HCT, which is fundamental to operation of this device, you can think of a polaron, which is a hole stuck on one little molecule in the organic, and an electron, which is delocalized over multiple lattice sites in the inorganic. So it's a little snowman that you would build in a cold Michigan winter. So now let's move on to looking at some device data. So we take our diode and we replace the inorganic with gallium nitride, the organic with DBP. And what this allows us to do is, because the gallium nitride is a wide energy gap material, wide band gap material, it can only absorb above 365 nanometer, while the organic can absorb everything from 365 to 650, which means that we can spectrally resolve the response of DBP from the gallium nitride. And putting 2 cathodes on this device, aluminum and gold, we extract charges out, and what we find is that there's clear indication that the exciton is reaching the organic and inorganic heterojunction and dissociating into free carriers. The spectra here, the photoaction spectra, matches the DBP absorption. And since this tightly bound state has to have a place to charge separate, this indicates that we're forming the hybrid charge transfer exciton. So we'll go one step further. And now I'll take out the DBP and I'll put in NPD, which basically has a larger energy gap. and that allows us to confine the charges at the hetero interface. So I'll increase these energy levels, and I'll start injecting charge. So I'll forward bias this device to 6 volts. Now, what happens now? So what we find in our emission spectra is right at room temperature, we see an emission that is spectrally resolved from the organic emission, and that corresponds to 750 nanometers or 800 nanometers, which is exactly the hetero interface offset. So this indicates that once we start injecting charges, we're forming this hybrid charge transfer exciton, and the recombination is occurring to this, through this state. So to understand these results better, we did some quantum mechanical simulations, and we find that there are 2 distinct states that we can predict. So there is the bound state where the electron is loosely confined to a hole in the organic, and this has only a 9 MeV energy, so we should not be able to see it at room temperature. And we find that if we're able to localize the electron right at the interface, we're able to force it to stay there, which might be possible if, for example, the semiconductor is defect-ridden, which gallium nitride is. We suddenly increase the binding energy to higher than room temperature, and we also increase the lifetime. So these 2 states in my previous 2 experiments that I showed you are observed by external quantum efficiency measurement and electroluminescence measurement. So we go one step further now. So we see an observation of the hybrid charge transfer exciton, but we have an uncontrolled observation. Basically, the defects are giving rise to emission from this hybrid charge transfer state. So can we control this state? Can we have systematic control? Because as I showed in my motivation slide, systematic control allows us to get things like 2-dimensional electron gas, solid-state lasing, all kinds of interesting things that are of importance for modern optoelectronics. So we go back to our simulator. We replace the gallium nitride with gallium nitride, indium gallium nitride. There's a quantum well here. And what we find is that the binding energy of the state increases to 165 MeV. So looking at this state further, we find that applying voltage to this state, we can actually tune the binding energy of this state, and we can also tune the lifetime of the state. Voltage which corresponds to field in the device. So as a result, we have this long-lived state right at the interface of organic and inorganic heterojunctions whose properties we can tune, whose absorption, emission, and lifetime are tunable by voltage. And this is exciting for optoelectronic applications. And just to confirm the existence of this state, I will show you two more. So we made gallium nitride, indium gallium nitride devices, and we did external quantum efficiency measurement. And what we find is that with the 11%, which has the wider band gap, and the 21%, there is a significant decrease in the EQE, which suggests that the electron is being bound at this, in this quantum well. We can go one step further. We can extract the change in EQE as a function of field in the device, and we find that it shows a systematic linear relationship with square root of the field, which is predicted by the Poole-Frankel emission theory. So the slope here is proportional to the dielectric screening by the quantum well, and the binding energy is proportional to the intercept at the field. And we find that the predicted value matched the fitted value, which suggests that the quantum well state is does exist. So in conclusion, in this work, I have confirmed the existence of the hybrid charge transfer exciton, the fundamental quasi-particle that's governing excited state dynamics in OI semiconductor heterojunctions. And this is the first demonstration of organic and inorganic hybrid quantum well, where the exciton properties are tuned using heterojunction dimensionality. And in the end, I would like to leave you with the possibility of what's possible with organic and inorganic hybrid semiconductors. So if I had maybe tenure as a grad student and I was here another 10 years, these are some of the projects I would consider exploring with OI systems. So inorganic lattices have, inorganic superlattices have been applied in quantum cascade lasers, in for example, as terahertz emission sources. So it would be interesting to make organic inorganic superlattices and start to explore some of the emergent properties that result from the strong coupling between the tightly bound exciton and the large radius exciton in the inorganic. So this could have applications in polaritons, in a lot of nonlinear optical phenomenon. And then this opens up, because of the low binding energy charge transfer state that exists at the inorganic-organic heterojunction, this opens up the possibility of new higher efficiency solar cell designs. And finally, there's the possibility of making an excitonic transistor, which because you can bypass the photon to electron conversion, because you can excite the exciton and use voltage to control the exciton, and then re-emit that right out of the right out of your device. So you speed up your information processing. With that, I would like to thank two of my group members, Xiao Lu and Ding Kan, for collaboration on this work, and thank the funding agency, and be happy to take any questions.
Excellent. Okay. Our next talk is going to be on large-scale flexible transparent electrodes using high-performance doped silver films. This is Chengyang Ji from Electrical Engineering. Please go ahead.
Thanks so much for the invitation to the presentation today. My name is Chengyang Ji from the Department of Electrical Engineering and working in Professor Lin Jie Guo's group. Today I'm going to talk about the novel flexible transparent electrode based on high-performance doped silver films and also its mass production. Traditionally, different conductive metal oxide are used for the transparent electrodes, such as aluminum doped zinc oxide and the indium tin oxide. Nowadays, emerging flexible optoelectronics require this kind of electrodes to be bent in any shape. And apparently, this kind of oxide cannot meet the requirement because of their poor mechanical flexibility. In addition, especially for the indium tin oxide, it has the issue of low transmission, especially at the near IR wavelength range. And the scarce and the pricey indium element in this material makes the manufacturing very high cost. Finally, both of the oxide here need a very high annealing temperature to achieve the both optical and electrical performance. And this is unsuitable for flexible polymer substrate. Actually, researchers do provide new selections for the transparent electrode. For example, the carbon-based material are used for the transparent conductors. However, this kind of material are limited by their conductivity, and it will be an issue when being applied in large-scale devices. People are also using like random metallic nanowire network and a regular metallic band mesh for the transparent electrode. The first row is the silver nanowire network, and the second row is the work about the periodic hexagonal silver metal mesh. However, this kind of material has very high optical haze because of the scattering from the nano and micro structures. And this is undesired, especially in the high-resolution display application. In addition, the non-uniform conductivity across the whole device and this rough surface will lower the device efficiency or even cause a shooting issue when being applied in the active devices like solar cells or organic LEDs. Another solution for the transparent electrode is using the DMD design, which is basically a sandwiched structure with the metal in the middle for the high conductivity. And both the top and the bottom dielectrics are used as an anti-reflection layer to suppress reflection and therefore enhance the transmission. So this design can solve all the issues mentioned before. It has very high conductivity because it gets metal involved, and the optical haze is very low. The conductivity is very uniform, and the surface is very smooth because this structure is only continuous films. It's very interesting. People find out the best transmission of this kind of DMD structure occurs when the silver film is 60 nanometer. Silver is typically used as this metal layer because of its low optical loss and high conductivity. It's kind of counterintuitive because we thought the thinner the silver is, the better transmission we will have. The discrepancy is because of a well-known issue of a thin silver film. When the silver film is very thin, for example, getting down to around like 10 nanometer, the silver becomes discontinuous, and this island morphology will induce additional absorption called plasmonic loss. That's why the thin silver film cannot be applied in the DMD for the high transmission performance. And typically, the DMD transmission is limited to around 80%. So here, we want to solve this issue, further enhance the transmission of the DMD by making the thin silver continuous again. This is achieved by adding a little bit copper doping during the silver deposition. So this is a 7 nanometer copper doped silver with a very smooth surface. And the AFM image further reveals the roughness mean square is only 0.4 nanometer, which is pretty small compared to this continuous pure silver film. And this so-called copper doped silver film is achieved by a process called co-sputtering. We spotted the copper and the silver target respectively in the sputtering tool. And all the process is finished at the room temperature, so this material is suitable for all kinds of substrates. The deposition rate between the silver and the copper is around 55:1. And this idea is inspired by our previous work, which is about the aluminum doped silver. We use 6 atomic percent aluminum to form very thin aluminum doped silver. But this doping ratio is much higher than the copper in the copper doped silver here. And we all know the aluminum has relatively low transmission in the visible wavelength range, and the conductivity of aluminum is also much worse than both silver and aluminum, both silver and copper. Therefore, this aluminum doped silver is kind of limited in terms of its optical and electrical conductivity performance. So the added little amount of copper here can successfully suppress the 3D growth mode of the silver growth. So by comparing the AFM image with the very thin pure silver layer, the copper added here can increase the nuclear density and also reduce the silver particle size. Therefore, this is very critical for the later on continuous silver film formation. This characterization method can be found in this published paper. And as I mentioned, the copper doping is so little, so especially compared to the aluminum doped silver. So the great performance of the silver itself, like the low optical loss and high conductivity, can be better maintained than the aluminum doped silver. So our copper doped silver have very high optical and electrical performance. For the 7 nanometer copper doped silver, the average transmission within the visible wavelength range is around 72%, which is much higher than the 7 nanometer pure discontinuous silver. And this here is the photos of the deployed 15 nanometer pure silver compared with 7 nanometer copper doped silver. Both are very transparent and smooth right after taking out from the chamber. But even after 30 minutes exposure to the air, the pure silver gets degraded and turn black like this. But the copper doped silver is still very shiny. Actually, myself kept copper doped silver deployed half a year ago, and it's still very good in terms of both optical and electrical performance. The dark appearance of the pure silver here is because of the previously mentioned plasmonic absorption of the silver islands. And our copper doped silver has very high conductivity. 7 nanometer film has the sheet resistance only of around 13 ohm per square. By comparing the permittivity between the pure silver and our copper doped silver, it's easily to find our new alloy film is very low loss. So the E2, the imaginary part, is proportional to the material absorption. And because of the low copper doping, the optical loss within the visible range is very similar between the pure silver and the aluminum doped silver here. And this is quite desirable for the transparent electrode later on. Because we wanted to apply our silver film for the flexible devices, so we did a bending test. The 7 nanometer aluminum copper doped silver film is deposited on the PET substrate with a thickness of 15 micron, and the bending radius is 1 millimeter with the inward bending method. So here's a comparison between our doped silver film with some commercial transparent electrode based on either silver nanowire or silver metal mesh. All the substrates have the thickness of 50 micrometer. And after 5,000 cycles of bending, the sheet resistance increased only 15% for our copper doped silver film. And it outperforms both the silver nanowire and the silver metal mesh in terms of the bending performance. And this is because of the ductility of the thin silver itself. We also incorporated our thin silver film in the DMD structure for higher optical performance. We use the zinc oxide here for the anti-reflection layer to induce the transmission. Actually, we have more freedom in selecting the anti-reflection layer. We can use any electro transporting layer or Hall transporting layer to accommodate the device requirement. We already adapt our silver film in both the organic solar cell and organic LEDs. And here is the measurement result and simulation result of our fabricated device. This shows very good, consistent. Our fabricated device in our own lab shows very high transmission, above 85%, which is around 94% when reference to PET substrate. The haze is very low because the continuous film, and the color is very neutral with the B value only around 1.7. The sheet resistance is around 10 ohm per square. It's very comparable with ITO. However, this is not the optimized structure yet. And before we apply our film in the real application, we need to make sure our film is stable enough. So we did a humidity test at 85 degrees C with 85% relative humidity with the protection of 3M barrier film. And both the optical and electrical performance are very stable after even 7 days test. So we have very transparent film, we have very conductive material, and we also solve the stability and the bending issue. So we are ready to the mass production of this product. We use the roll-to-roll sputtering tool to achieve very large, flexible, transparent on PET substrate with a rolling speed of only about 12.5 meter per minute. And this is the small pieces cut from the large samples. We also use the sample for the touch panel demonstration. 2 pieces of samples are laminated with the OCA adhesive layer, and laser patterning is used for the metal structures, the mesh structures. And here's a video showing our device is working well under the bending status. So in summary, we have proposed ultra-thin, smooth, and low-loss optical loss silver film with a little bit copper doping. We have used this silver film for high transparency DMD structure, and we also proved the scalability of this material with roll-to-roll sputtering method. Here's a summary table of our material performance with very high transparency, low haze, low resistance, and a very neutral color. It's very stable under both the chemical test and the bending test. The hardness is higher than 3H, and there's no change after the humidity test, very harsh humidity test of 85 degrees and 85% relative humidity environment. And we can control the non-uniformity below 5%. So for future plans, we already have an even better design with absolute optical transmission around 95% and a very stable material. So we will try faster rolling speed with around 4 to 5 meters per minute and on a large substrate. And that's it. Thanks for your attention, and I'm happy to take any questions.
All right, we'll get started with our next presentation. Excuse me, can we get started? All right. This is our next speaker, Saeed Kazmi. I'm probably going to screw up your name.
Kazemi Apnavi.
Thank you. From mechanical engineering. He's going to be talking about unveiling the intercalation mechanism in core shell cathode particles for lithium batteries. Saeed, go ahead.
All right, hello everyone, and thanks for the introduction, and thanks, I would like also to thank the organizers of this symposium for giving me this opportunity to present my work here. I'm a PhD student in Professor Thornton's group, and today I will be talking about our research on core shell cathode particles for rechargeable lithium batteries. So over the past couple of decades, we all know that how important rechargeable batteries have become because they have become a reliable power source for a wide range of applications, from larger scales such as in electric powertrain systems to smaller scales such as in consumer electronics, in laptops and cell phones that we use day to day, and even smaller like medical devices. So really, the motivation behind this work was to develop new cathode materials with enhanced electrochemical performance. And one of the most common techniques for doing so is to coat the surface of the cathode particles with another active material to present some new properties or improve, in general, the electrochemical performance of the particles. So the cathode part of a rechargeable battery is made of small, sometimes nanoscale or microscale particles. And sometimes in order to, for instance, prevent side reactions of the active material with the electrolyte, or to improve the thermal stability and even facilitate the carbon coating of the particle in order to improve the electronic conductivity, people do coat their particles with another active or inactive material. And our focus for now is on coating the particles with another active material. However, we can't just go ahead and choose two different materials and combine them together and say we have a new hybrid cathode materials. What we're really trying to understand is how these different thermodynamic and kinetic properties of the active materials affect the electrochemical performance of the cathode. And in order to do that, we need to look at what is happening inside the battery when you charge and discharge it. So when you discharge a battery, the cathode particles become lithiated, for instance, in a lithium-ion battery. And when you charge it, the cathode particles become delithiated, and the lithium just goes back to anode. And so really the answer to this question lies in the mechanisms of the lithium transport inside the cathode particles, which itself is a function of what is called the open circuit voltage of the active materials, which is the electric potential in the absence of current, and also the lithium diffusion coefficient inside the particle as a kinetic factor. So our ultimate goal here is to determine a design criteria based on these material properties, such as the OCV or the diffusion coefficient, in order to build new cathode materials, hybrid cathode materials with improved electrochemical performance. And so in order to do that, as I said, we need to look at the lithium transport inside the cathode particle. So we went ahead and constructed a fairly simple model of a cathode particle, and we assumed the particles to be spherical so that we can describe the dynamics using one-dimensional equations. And this will help us in terms of computational efficiency. And so here you can see a model of the cathode particle which has a core material. We call it the bulk phase, and it has an open circuit voltage of, let's say, V0, and it's fixed. And the core material is encapsulated in a second phase, which is called the surface phase, with a shifted open circuit voltage. So I need you to keep that in mind because we're going to refer to this quite a few times during this talk. And so there is a difference in the OCV of the bulk phase and the surface phase, and it's the omega. And that's actually the reason behind the characteristic of these core shell cathode particles. So we modeled the charge transfer reaction at the particle electrolyte interface and the lithium transport inside the particles with linear diffusion. And we also assumed constant diffusivity in the surface and bulk phase to further simplify the model. And so the nice thing about this model is that it's, as I mentioned earlier, it's computationally inexpensive. So it allows us to perform parametric studies in order to find the optimal material properties for certain performance. So before I get into too much detail of the results, let's see what is actually happening inside these particles when you charge and discharge them. So in the figure to the left, it's the voltage versus depth of discharge of a particle. So you will see how the voltage is changing as the particle is becoming lithiated. And this figure to the right shows essentially the lithium concentration or lithium side fraction as a function of its distance from the center of the particle. So when I discharge the particle, as you can see here, the surface phase becomes lithiated first, and then the bulk phase. So the reason is that, if you remember, I mentioned that the surface phase had a higher open circuit voltage. Therefore, thermodynamically, it is more favorable for the surface phase to become lithiated, and that's essentially what is happening here, until the chemical potential in the surface phase and the bulk phase are equal to each other, and that's when the bulk phase can also lithiate. But because once the surface phase becomes full, the lithium transport becomes limited because the mobility of the lithium becomes very small. So it doesn't allow further lithiation, and therefore we won't be able to use up all the capacity that we could have in a core shell cathode particle. So this is telling us that it's better for us to minimize this voltage difference, this OCV difference between surface and bulk phase, in order to improve the capacity of the cathode. And the exact reverse thing happens during discharge. When you discharge it, the bulk phase actually starts delithiating first because it had lower voltage, lower OCV, so it's thermodynamically more favorable for the bulk phase to delithiate first, and then the surface phase. As you can see here, if you look at the discharge and charge curves, you can see that it shows a two-stage lithiation and delithiation process. And that was because the first one was, the first part of the discharge curve corresponds to the lithiation of the surface phase, and then the second part for the bulk phase, and then the reverse thing for the charge curve. So now we can see that having an OCV difference between surface and bulk results in a reduction in capacity, and it's actually more if we increase this voltage difference. We also looked at the effect of charge-discharge rate. As many of you may know or may not know, the discharge capacity almost always decreases by increasing the charge-discharge rate. So this means that the faster you charge or discharge your battery, you will get lower capacity. And this is the same thing for core shell cathode particles. However, in the cases where the voltage difference between the surface and bulk is higher, which is the red curve here, you can see that the reduction in capacity as we increase the charge-discharge rate is much more significant. So this is again telling us that having an OCV difference between surface and bulk will make it more sensitive to C rate, which is again not good. So again, what we'll learn here is that we need to minimize the OCV difference between the surface and bulk of these particles. We also looked at the effect of the surface phase diffusivity as a kinetic factor. And as you would expect, the discharge capacity increases by increasing the surface phase diffusivity, which is good because now we know that we might be able to actually compensate for that capacity loss because of the OCV difference by having a surface phase that has a higher lithium diffusion coefficient. And that's what we did. So we looked at the discharge capacity. We looked at how discharge capacity changes by increasing the voltage, the OCV difference. As you can see, as I mentioned earlier, discharge capacity decreases as you increase this OCV difference. However, the amount of decrease is much smaller if you increase the lithium diffusion coefficient in the surface phase. So So this is telling us that we can actually recover some of that capacity loss because of the OCV difference by utilizing a material that has a higher lithium diffusion coefficient in the surface phase. So in summary, what we learned from this study was that we observed a reduction in capacity because of the OCV difference and small surface phase diffusivity. And this reduction in capacity shows itself actually is actually much higher at higher C rates or higher charge discharge rate. However, we learned that this reduction in capacity can be recovered by using a material that has a higher lithium diffusivity in the surface phase. So these findings in general will guide us in the material selection for designing hybrid cathode particles. So instead of just randomly choosing different materials, we can wisely choose the material for the core phase and the surface phase in order to have the highest possible electrochemical performance and highest capacity. And in continuation of this work, we are also looking at the geometrical effect of the cathode particles, including the effect of the surface phase thickness, and also we are performing 3D simulations to study the effect of particle shape. And here in this figure, you can see this is a hexagonal bipyramid cathode particle, which I've cut through so that you can see how the concentration changes inside the particle. And again, you'll see that surface phase and bulk phase similar to the spherical particles, but in order to see if the capacity or the performance changes, we need to perform further studies to confirm the effect of geometry. And at the end, I would like to acknowledge our funding source from Northeast Center for Chemical Energy Storage, which is funded by the Department of Energy, Office of Basic Sciences. And for all these simulations, we use the Flux, which is our supercomputer at University of Michigan. And thank you, everyone, for your attention. If there is any question, I'll be back.
All right, now we'll get started with the last talk of this session. This is from Alan Olvera, who's a graduate student in material science and engineering, and he'll be talking about partial Indian solubility induced chemical stability and colossal thermoelectric figures of merit.
There you go, yeah. Well, my name's Alan Olvera, and I've been working in the Tuteja group for the past about 5 years. And let's get started. So for those who are not familiar, copper selenide, Cu2SC, is a thermoelectric material, which is a superionic compound above around 400 K. And for that, in that region, it performs very well. As you can see here, the ZT, which is proportional to the efficiency of the material, surpasses about 1.0, which usually is a benchmark for many thermoelectric materials. And at around 1,000 K, reaches about 1.5 ZT. And the reason why it can obtain such a high ZT is because of the superionic mobility in the compound. So you can see here in this molecular dynamics study by Kim et al., here in the purple is the displacement of copper ions at about 500 K. And as you can see, it's very little localization of copper. So there's large displacement in where copper is. And at even greater temperatures like 1,100 K, there's almost no distinction of where copper remains in the system. And for that reason, we have a very low thermal conductivity and can increase this ZT. However, when we apply a current to this material, as you can see here, what ends up happening is that the copper ions, which are positive, deposit on top of the negative terminal. And this has been seen in several works. In some cases, very minimal copper ion diffusion has been seen. But under extreme current densities, you can have very large amounts of copper leaving the system. So in order, even though the ionic mobility is a benefit for increasing the ZT, and in fact is a huge detriment when we want to consider this in commercial application. So in order to potentially solve this problem, if we look at the cubic structure, which is the superionic structure of copper selenide, and we imagine entering some foreign atoms here, well, essentially what we can do is reduce the mobility of copper, or at least the mean free path of copper ions in the system, while also adding bridging networks here in these foreign atoms and increasing the charge carrier mobility. So our approach to this was to create a composite between copper 2 selenide and copper indium selenide. And the reason why we use copper indium selenide is because it has an extremely similar structure to that of the extremely similar high temperature structure to that of copper selenide. And also it's been shown that the indium atoms have a stronger ionic bond in this system. Now, when we look at high concentrations of indium nanocomposites, we can see that there's large agglomerations of grains here, around 10 to 20 microns under SEM. But when we take a closer look in TEM, we can actually see that these agglomerations are actually even smaller agglomerations of small copper indium selenide nanoparticles. On the other end, at low concentrations, such as 1% and 3% indium, we actually see that indium is soluble in copper selenide, so we don't see any formations of these grains, and we have a nice homogeneous crystal structure, at least when we're looking at it in TEM. But in either case, if we have copper indium selenide as a nanocrystal or a localized point defect, we can imagine that it could inhibit copper diffusion through that system, as well as stop some phonon propagation, but at the same time allow carrier diffusion, since the nanocrystal and the surrounding matrix share such similar structures. Now, when we look at the electroconductivity, we can see that here for the pure material, copper selenide, we get a huge increase from even at 0.5% indium and 1% indium, at maybe around 4 times higher than what it originally was, and we see a conversely or a proportional decrease in the Seebeck coefficient. Now, normally, the electroconductivity, as we know, is proportional to carrier concentration, and the Seebeck is inversely proportional to carrier concentration. So in a lot of materials, this phenomena where we see an increase in the electroconductivity and a decrease in the Seebeck coefficient is mostly attributed to an increase in the carrier concentration. However, when we measure the carrier concentration and plot it correspondingly with the Seebeck coefficient as a function of indium concentration, we see that the Seebeck coefficient is proportional to the increase or decrease in carrier concentration. So we can't attribute the fact that we have a carrier concentration dependent increase in conductivity. Now, instead, if we plot the carrier mobility of the systems here, specifically looking at the 1%, pure material and the 1% mole indium percent sample, we see that we get a huge increase in the carrier mobility with a similar charge temperature dependence on the mobility. However, after the phase transition, we actually see that the mobility of the pure sample starts to drastically decrease, meaning that the temperature dependence, or also showing that the temperature dependence is much steeper because of that superionic mobility that's causing carriers to be scattered. On the other hand, the 1% sample does not show such an effect, and we are attributing that to the fact of, as I mentioned earlier, that the indium ions in the system can enhance the charge mobility of the material. Now, looking at the thermal conductivity of these samples, all materials show a relatively low thermal conductivity around 1, specifically where the 1 and 3% samples are showing an extremely low thermal conductivity of about 0.5. And we can explain this by looking at the specific heat capacity. So as you can see here in this inset, after the phase transition from 400 to about 750 K, we can see that for the pure sample, we see a steady decrease in the specific heat capacity. Now, this is not a normal trend for heat capacity, but for this specific material, because it's a superonic, has a superonic capabilities, it decreases in specific heat capacity due to the fact that there's a lowering of the degrees of freedom in the system. And there's an even greater effect in the 1 and 3% sample here. And we attribute that, that reduction in degrees of freedom to the much lower thermal conductivity. Now, combining the electrical components, we calculated the power factor, which is just the top portion of the ZT, so it's electrical conductivity times the Seebeck squared. You can see that for all materials, compared to that of this black line here, we get a much higher or a much larger power factor, especially for that of the 1% sample. And combining that with the thermal conductivity, we actually get a huge increase in the ZT of the 1 and 3% samples, approaching nearly twice as much as this reference here. So if we look at 850K, it's about 1.0, and we are achieving about 2 to 2.5 ZT. Well, despite that, even though we have a good ZT, it may not matter since the material is inherently unstable under high currents, especially at temperatures above the superionic transition. So we performed an electromigration study where we applied a heat of 250 degrees C, which is about 100 degrees C over the superionic transition temperature, and also applied a current density of about 100 amps per centimeter squared for 24 hours. So that's about 8 times higher than the normal operating temperature, which is 12 amps per centimeter squared. Now, looking at the first 30 minutes of this test, on the left here is the pure sample. And almost immediately, within the first couple minutes, we start seeing the formation of these dark masses on the left here. On the other hand, if we look at the indium-modified sample, we do not see the formation of any of those masses on the negative terminal. In both cases, we do see some kind of oxidation effect because this is done at 250 degrees C at room temperature. But looking closer at the negative terminal of both the samples, we see that there is a few large masses, noticeable large masses on the pure sample, while there's nothing on the modified sample. And this dark region here is just graphite foil that was used to increase the ohmic contact in the testing setup. Now, taking a closer look, these masses actually consist of some sort of micro wires here of copper, and there is oxygen, again, because this was oxidized and done at room temperature. But you can see that there's very little to no selenium, and some of this is some more of that carbon film. And this is very similar to what's already previously been observed, so this is nothing abnormal. We definitely expected it. On the other hand here, if we look at elemental mapping and backscattered imaging of the pure sample, we can see that there's more or less homogeneous distribution of copper, selenium, and indium. And the reason why you can see some differences here is because there was delamination of the oxide film on top of when this graphite foil was removed. So in summary, we have copper selenide and copper indium selenides can be easily synthesized as nanocomposites using the templating method demonstrated here and previously published work. And also, we can show that indium doping is enhancing the ZT of the material from 1.5K at 1.5 at 1,000K to 2.5 at 850K. And lastly, and most importantly, we show that indium stabilizes copper migration under extreme current densities, which opens opportunity for the commercialization of copper selenide. And I will say that in all the other samples I measured, including the 3%, 10%, and 30%, I still did not see any of these masses forming on the negative terminal of the device. So with that, I want to acknowledge my group and Professor Steer at Uher's group, and my funding from the Department of Energy and Rackham Graduate School and Michigan Materials Characterization Center. Thank you.